Good morning, students. So we'll continue with the next one topic, that is a protocol implementation issues. The way the application programs interact with the underlying network is similar to the way a high level protocol interacts with the lower level protocols. Say for example, the TCP needs an interface to send a outgoing message to the IP, and IP needs to be able to deliver incoming messages to the TCP. Now if you are going to see this particular the layered architecture, in this layered architecture you are having a different layers are there, and the information has to be processed by the each layer, and each layer you are going to assigning some task. According to the task, the message is going to be treated, and then it is going to be forwarded to the next layer. Now you are having the two types of the messages are there. One is the inbound message, another one is outbound will be there. So inbound is that the messages which you are going to be receiving from the network. So here in this particular process, the information has to be processed from the bottom layer to the top layer, and the next one in the outbound, here it is that the message has to be transmitted from the topmost layer to the bottom layer when you are sending the information from your system to the network. Now how exactly this message is going to be transmitted, and how these particular messages are going to be treated or the processed, so this is the question here. Now if you are going to see this, we need a proper interface will be there, that is to send the information from one layer to the another layer. This is exactly the service interface, since we already have a network API, that is the sockets will be there. Okay, now here we are going to see about that the process models, that is to process that a particular the message, we need the processes, it has to be executed in the system. These processes or the threads is created by the operating system. It is the responsibility of the operating system to create this particular process and assign the resources which is required for the execution of the process, such as the address space, CPU cycles, and etc. Okay, now these processes are going to executing the task which is allocated to each particular the layers. Now how it is going to be executed, now we are going to see that you are having a two particular the models are there. One is the process per protocol, another one is a process per the message. Now if you are going to see this particular the diagram, here it is the two models, one is a process per protocol, another one is a process per message. So in this what happens here, it is that each protocol is implemented by the separate process. Whenever the message is going to be arrived at a particular layer, where that a protocol is going to be execute, or it has to treat that a process, it has to sorry it has to treat that the message. So now each protocol is implemented by the separate process. This means that a message moves up and down the protocol stack. The process that implements the protocol I processes the message, and then that processor message is passed to the next one, another protocol. Either it may be the protocol I minus 1, or either it may be the protocol I plus 1. It indicating that the processor message has to be transmitted to its upper layer, or either it may be transmitted to its below layer, depending upon the message, whether you are transmitting or whether you are receiving the information. Okay, so how one process per protocol passes a message to the next process plus protocol depend on the support the OS provides the inter-process communication. So whenever you are having the messages to transfer in this, the message is going to be transmitted to the each layer. In the each layer, for each particular protocol is going to be executed by the separate process. So each process is going to process that message, and then that process message will be sent to the either the upper layer, or either it may be to the below layer. That is if you the process is executing the ith protocol, then it is going to send it to the protocol I minus 1, or either it may be the protocol I plus 1. So this is what you are going to be call it as a process per protocol. The next one here it is that process per message. So now here what happens is that whenever any information either you are sending or receiving, whenever the message is going to be arrived here, so for each message one process is going to be created until that complete process of that message is done. That is, if you are sending the message, the complete process of that message has to be transmitted from all the layers from top to the bottom, and from the bottom it has to be transmitted to the physical media. So until that complete process is going to be attached to that message. Okay, so now the process per message model treats each protocols as a static piece of code and associates the processes with the messages. That is, when the message arrives from the network, the OS is going to dispatch a process that it makes responsible for the message at it moves up the protocol graph. At each level, the procedure that implements the protocol is invoked, which eventually result in the procedure for the next protocol being invoked, and so on. So for the outbound messages, the application processes involves the necessary procedure calls until the message is delivered. In both the directions, the protocol graph is traversed in a sequence of procedure calls. As you know that it is the responsibility of that particular process to transfer the information from topmost layer to the bottom layer when it is the outbound message, and when it is the inbound message, so to traverse this particular message to all these layers to move from bottom layer to the topmost layer, at each layer the respective procedure call it is going to make it, and that it is going to be executed on the message, and that processor message once again it is going to be passed to the next layer. So once again it is going to call the procedure, and then it is going to be executed. So this is only one process is responsible for that a complete message has to be moved from the topmost layer to the bottom layer, or either it may to move from bottom layer to the topmost layer. So this is all about this process models. So the next one here we are going for the another one, that is the performance. This is the last topic of the first module. So in this we are going to be see about that uh, the important to understand the various factors that impact the network the performance. So now here is a saying that first get it right and then make it fast. Now you are going to be see about two important measures are there. The first one is the bandwidth, another one is the latency. The network performance is measured in the two fundamental way. One is a bandwidth, also we are going to be call it as a throughput. Another one is a latency. Latency is nothing but it is a delay. Now you are going to be see that what you mean by the bandwidth. The bandwidth of a network is given by, that is a number of bits that can be transmitted over the network in a certain period of time. So that is what we are going to be call it as a bandwidth. Say for example, a network is having a bandwidth of 10 million bits per second. So that is what you are going to be call it as an mbps, meaning that 10 million bits per second, or mbps, meaning that it is able to deliver 10 million bits every second. It is sometimes useful to think of a bandwidth in terms of how long it takes to transmit each bit of a data. Okay, now we are going to see about the another one, that is a latency. What do you mean by the latency? So this is the another one, the performance metric, that is the latency. Latency corresponds to how long it takes a message to travel from one end of a network to the other. The latency is measured strictly in terms of a time. It is nothing but the delay, the time taken by the message to move from one point of a network to the another point, or you can say that the time taken by the particular message to move from a source to a destination. So that is what you are going to be call it as a latency. So latency you are going to be measured in terms of a the time. So for example, here they are given, that is a transcontinental network might have a latency of 24 milliseconds. That is, it takes a message 24 milliseconds to travel from one end of North America to the another end. So it is going to be take a 24 milliseconds. This is the latency or the delay or the time taken by that particular message to move from one end of North America to the another. Now you are going to be see another one, that is RTT. RTT is nothing but it is a round trip time. So that is nothing but how long it takes to send a message from one end of a network to the other and back. So this is also, we are going to be call it as a two-way latency, or you are going to be call it as a two-way delay. Time taken by the message to reach from source to destination, and the time taken to reach the acknowledgement from destination to the source, that is what we call it as a two-way latency or the two-way delay, or we call it as a RTT, that is a round trip the time. Okay, now we are going to see that how to calculate the latency. So here is the formula to calculate the latency. So latency is equal to propagation plus a transmit plus a q. So now how you are going to calculate the propagation? Propagation is calculated, that is the distance divided by the speed of the light. Distance divided by the speed of light. As the light travels at 3.0 into 10 raised to meter per second in the vacuum, 2.3 into 10 raised to 8 meter per second in the cable, 2.0 into 10 raised to 8 meter per second in a fiber. Okay, now the next one we have to find the transmit. Transmit is equal to size divided by the bandwidth. Now we are going to be see these terminologies. What is the distance? The distance is the length of the wire over which the data will travel. Speed of light is the effective speed of light over that wire. What is the size? Size is the size of the packet. Bandwidth is the bandwidth at which the packet is transmitted. Now q terms are not relevant, so here the latency is going to be corresponds to the propagation delay only. Now the next one here we are going to find that how to find the volume of the pipe, that is through which the media through which you are going to send the information from one end to the another end. So how you are going to find the volume of the pipe? Now the volume of the pipe is finded by using the delay into bandwidth. So here it is that the latency corresponds to the length of the pipe, and the bandwidth gives the diameter of that particular the pipe. So now the delay into bandwidth, so that is the delay into bandwidth, the product gives the volume of the pipe. What is this? This is nothing but the maximum number of bits that could be in a transit through the pipe at any given instant. So this is what you are going to call the volume of the pipe is equal to delay into bandwidth product. Okay, now we are going to see the some of the examples. The different types of the links are going to be available. What is the bandwidth available, at to what distance they are used to communicate, what is the RTT, and what is the delay into bandwidth. So here if you are going to see about this, that is the dial-up connection will be there. The bandwidth is 56 kbps, distance is up to 10 kilometer. So round trip delay will be there, it is on my seconds, and delay into bandwidth is a 5 bits will be there. So you just see it here. For the similarly we have written for the wireless LAN, satellite, and cross country fiber will be there. Okay, so that is the 10 gbps, it can be distance is up to 4000 kilometer, and the 40 milliseconds will be there. And the delay into bandwidth here it is up to 400 MB. Okay, so this is here all about the different types of the links and all. Now if I want to find out the throughput, what do you mean by the throughput? The bandwidth that is available on the link and the number of bits per second that we can actually transmit. See here, this is the difference between that actual number of bits which is transmitted over the link in practice. That is what you are going to be call it as a throughput. The effective end to end throughput that can be achieved over the network is given by the simple relation, that is the throughput is equal to what is the transfer size divided by the transfer time. Now here you are going to find that transfer time. How you are going to find the transfer time? Transfer time is equal to RTT plus 1 divided by the bandwidth into the transfer size. Okay, so here is a one example. Say for example the user want to fetch a 1 MB file across a 1 Gbps network with a RTT of 100 ms. So the transfer time here they have given RTT is 100 plus 1 divided by 1 Gbps into 1 MB. So here it is that 108 ms. So throughput is equal to what is the throughput here? Transfer size divided by the transfer time. So what is the transfer size? It is 1 MB. What is the transfer time? It is 108 milliseconds. Divided by that is 74.1 Mbps is the actual throughput. Okay, So this is the actual number of bits transmitted over the link. So this is all about this particular uh, the throughput. And the next one is that how to calculate the latency, what do you mean by the volume of the pipe, and all these things. So this is going to complete the first model. Okay, this, thank you very much.